The Agenda in the Summer with Nam Kiwanuka is made possible through generous philanthropic contributions from viewers like you. Thank you for supporting TVO's journalism.
The Big Dipper, the Seven Sisters, Saturn, and Mars. Wonders in the summer night sky are eternal. All week we'll find out what's out there with astronomer Bryan Gaensler, astrophysicist Nathalie Ouellette, aerospace engineer Walter Stoddard, and physics and astronomy professor Matthew Johnson.
We are now heading into the final frontier. For the next half hour, we're going to be talking about the universe. But before we start, when we had our little break, Bryan, you said something about the black holes that I, as a proud Canadian, I needed to get on record. What did you say about the black holes?
So I think what a lot of people in Ontario and Toronto don't know is that the very first black hole discovered was discovered using the David Dunlap Observatory in Richmond Hill. So we now know of huge numbers of black holes, but the very first one was right here in the GTA.
That is so cool. And I wonder too sometimes, because we know about the States, we talked about this the last show, we know about the States and their contribution to space, but we know very little about Canada, or the contributions that we've had, we kind of downplay them a little bit. What do you think we need to do to change that?
Everyone should watch your show.
There's a whole... Oh, sorry, go ahead.
No, please.
I was going to say, I mean, a few years ago, the Nobel Prize in Physics was given to 2 European astronomers that discovered the first exoplanets. But, I mean, Nathalie's probably best placed to describe some of the sad sort of story about what could have been in terms of Canadians who claimed the first exoplanets and then retracted it.
That's
and
right.
They were right?
Yeah, exactly. Yeah, so the Nobel Prize went to a discovery from 1995, which was sort of like, when it came out, it was confirmed, and this is the first exoplanet we've discovered. But there were some sort of tentative possible candidates in the late 80s, early 90s, and some of those contributions were from Canadians, but they were a little bit too cautious. They retracted it at some point, but it was later confirmed. So
what a missed opportunity, right?
Yeah.
Well, today we are going to be talking about the final frontier. And I have another image to show. This is from the James Webb Telescope's Deep Field. It's an image of thousands of galaxies and includes the faintest objects ever observed in the infrared. I'm noticing some of the light is bent around the center. Nathalie, what's happening in this image?
So much is happening inside this image. So there's 7,000 galaxies inside this image alone. And so you might think, okay, well, this is going to span a huge part of the sky. But the surface that represents in the sky is as big as a grain of sand on the tip of your finger, held out at arm's length. And inside that grain of sand are 7,000 galaxies. So we see how rich the universe truly is. And we sort of started seeing a glimmer of that with Hubble, who took its own deep fields. And we discovered all these new galaxies. But we're seeing even more with the Webb telescope because, again, the magic of infrared. So we live in an expanding universe. And as the universe is expanding, the galaxies are also going away from us. And they're shining light in the visible light and blue light. But as they are shining light and moving away from us, that light is actually being stretched out and turns red and turns infrared. So the very earliest galaxies ever created in the universe, from our viewpoint, can only be observed in the infrared. So the very, very earliest galaxies that we can see in this image would have been invisible to Hubble. We can only see them for the first time using Webb's infrared eye, and that is really exciting.
I mean, this might sound like a dumb question, but I guess there's no such thing as a dumb question.
Yeah.
Just the role technology plays in this, because earlier, in one of our earlier discussions, you mentioned that, you know, the Hubble technology from the 70s and the images that we were able to get, but now we're getting better images. So how do scientists know, I guess, what kind of technology to pursue, or what kind of technology will give us a better picture of the universe?
Often We can use technology that already exists, but sometimes we're the first people to ever ask these questions. So the engineers and the scientists need to innovate and invent completely new technology that is first and foremost for these scientific goals. But lo and behold, they end up having unexpected benefits for daily life. So Wi-Fi was invented by radio astronomers, for example, or the cameras in our smartphones are spin-offs of the cameras that we developed for space telescopes like Hubble. So astronomy is actually serving society quite well.
The other thing is that when you see these beautiful pictures and that gets all the attention, what you don't see is that 20 or 30 years before that, at universities, and I know that at Nathalie's institution, University of Montreal, and at my University of Toronto, there are people not in the headlines who are saying, oh, I read in a magazine about this cool new tech. I'm going to buy one of those, and I'm going to put it in my lab and pull it apart, and I'm going to see if I can make it do something for astronomy. And half the time it's like, no, that was a terrible idea. But half the time it's like, oh, wow, we can measure light or study things in a new way. And then 20 years later, you get these spectacular new ways of studying the universe because of people tinkering in their labs. And I think one of the things that Canadian scientists do really well is to sort of ask these off-the-wall questions about technology at a very early stage that eventually becomes sort of the standard cameras and detectors that we have in our telescopes.
And not just the technology, but the software behind it. I mean, there's innovation there too. For example, we're in the midst of an artificial intelligence revolution, and part of that image is, well, how do we dig into it and get all of the information we might possibly be able to learn? So to give you an example, there were the streaks you saw. That is the light from distant galaxies being bent around galaxies that are a bit closer to us as the light comes on its way. And there is so much information about the galaxy that does this lensing of the distant galaxy if we could only understand the pattern better. And that's one great application of image processing techniques and artificial intelligence, learning how to reconstruct the intervening thing that did the bending of the light, and then learn about that thing itself.
And Walter?
Well, that question about technology and needing to invent it, right? Like we were talking after yesterday's conversation about gravity waves. And in order to measure them, in order to detect them, we needed to build interferometers, right? 3 kilometers long, if I'm not mistaken, and perfectly aligned mirrors so that these lasers could bounce and you could measure changes in length, I think smaller than an atom.
Yeah.
So that's incredible, and it required that kind of precision. So, but we had the idea that, well, gravity waves exist, and if they exist, well, they should be able to measure it, right? So you build it and then see if it works.
Well, we have another image that I'd love to get your thoughts on, and this one has been captured also by the Webb telescope. It's Stephan's Quintet, a cluster of 5 galaxies. It was an exceptionally large image covering 1/5 of the moon's diameter, contains over 150 million pixels and almost 1,000 separate image files. It was captured by Webb's near-infrared camera and mid-infrared instrument. Brian, what is the significance of this image?
Well, I think first and foremost, it's a beautiful image. Like, it looks fake. It looks like an artist's impression, but it's a photograph. And if you had really big eyes, this is what you would see. I think what it tells us, it's a vital sort of imprint of what actually is happening to galaxies over time. You sort of think of a galaxy as sort of sitting there in space as just a static thing. But most galaxies are in groups. There's quite unusual to have a galaxy by itself. And when you're in a group, you are orbiting the other galaxies and interacting with them. And that's sort of one of the basic building blocks of the universe. So our galaxy is in a group. We not very imaginatively call it the local group. And this is a more tighter, like more packed in group than ours. Ours doesn't look like this. But it shows you that if you want to understand a galaxy, you have to understand its neighborhood, and you have to understand all the galaxies around it who are like attacking it with their gravity. And sometimes galaxies collide or merge, and sometimes they have a near miss. And this is sort of essentially like a traffic jam or even a traffic accident where multiple galaxies have sort of come together.
So there's a lot of movement.
Yes, so these galaxies are moving in very complicated ways. We don't see that because the movements are actually very fast, but they're so far away that they look frozen in time. But we can do spectacular computer simulations of what happened before. We can sort of backtrack how these galaxies got to this point, and then we can run the simulations forward as well. And the reason these galaxies look the way they do is because of their interactions. And so images like this really help us understand our own Milky Way, which itself, a Milky Way is a cannonball. It's eaten lots of other galaxies over its lifetime. It's in the process of eating more galaxies right now. And this is sort of, in a cooking show where you can sort of say, here's one I prepared earlier. This is sort of showing us, perhaps what was going on in a Milky Way-like galaxy a long time ago.
Natalie?
So even though I work at an exoplanet research institute, I actually study galaxies and galaxy evolution. So this is my second favorite image from Webb. I love this image.
Yeah.
And so, yeah, you can see some galaxies that are actively merging. And that sounds, a lot of the terms we use for galaxy evolution are quite violent. Galaxy harassment or cannibalism.
What is cannibalism?
Where you have a large galaxy eating smaller galaxies. And so that's why Bryan mentioned that the Milky Way is a cannibal. It eats other galaxies. But something that does happen in that destruction is the creation of new stars. And you can actually see that in this image. There are two galaxies that are just at the point of fusing together, but there's one on top, and it's colliding into that duo. And you see this shock wave of orange, and that is the gas envelopes of the galaxies that are hitting each other, and they're compressing. And that gas is creating new stars. It's like fireworks igniting new stars. So even though there's all this destruction and the galaxies will come out of it looking completely different, it's creating all these new stars through that process as well.
So from death comes life.
Exactly.
But the other thing, of course, is the galaxy is mainly empty space. So the individual stars aren't crashing into each other. So I sort of feel like there needs to be a little caption at the bottom that says, no stars were injured.
You shouldn't imagine two cars crashing into each other. It's like two ghosts passing through each other.
Okay.
Yeah.
Or pouring two buckets of sand into a new bucket.
Bucket. Matthew?
Well, it's also our future because we're going to collide with the Andromeda Galaxy someday.
You say that so casually.
Yeah. Well, don't worry, right? Yeah, don't worry.
It's like, what, 5 billion years from now?
Yeah, it's billions.
Our sun is going to cause more trouble before we get to that point, though, when it starts dying. So,
Walter, what do you make of that image?
It's a gorgeous image, and this is a new image, right? Very exciting. I think 1,000 different separate images were stitched together to make this, which is incredible. Again, the idea of the software necessary to do that, the computing power. But we've taken images of this before, and anyone remember It's a Wonderful Life? I recommend it. Beautiful.
Christmas time movie.
Yeah, It's a Wonderful Life. And so it opens with the angels talking, and they use an image of these galaxies to represent the angels speaking to each other. And so they flash and speak and plan their intervention.
Well, I want to talk about the Big Bang, but not like the TV show. What is the Big Bang, Walter?
You mean the
Big Bang Theory?
As in the start of everything?
Yes.
So it's the description of where the understanding of everything begins, right? Begins in singularity, right? Where we said that yesterday, where our equation goes to divide by zero error. So everything starts and then expands from there, and we actually can't see it. So there's a point where the universe is too energetic, and light is bound. So light, matter, it's all the same thing. It's all this big soupy mess. And then finally, it cools enough that light we can finally see. So we actually can't see the start. We can only see where light was available. That's where gravitational waves are exciting, because maybe we can listen if we can't see.
So what is the big bounce?
The big bounce. So it's a way of patching up that divide by zero and asking, well, what happened before, if it even makes sense to think about a before. And well, we know we're expanding from a state of infinite density. And so, well, maybe one thing that happened before is we collapsed into a state of infinite density.
Well, and just to follow up on that, in 2015, there was news that we were able to observe gravitational waves. Can you explain how we measured that?
So this was an observation by LIGO, which is an interferometer that Walter was mentioning earlier. And what happens when a gravitational wave passes through you or stuff or an interferometer is that it alternates between stretching and in one direction and squeezing, in the opposite direction, and then stretching in this direction and squeezing. So it's like you can't see that on the camera, but anyway, stretching and squeezing. And so what happens to this interferometer is it's got two perpendicular arms, and while one is squeezing, the other one should be stretching. And we measure that differential length, as was mentioned, to within the size of an atom. So this is incredibly small stretching and squeezing. And we think that these gravitational waves were sourced by the merger of very distant, extremely massive black holes. So that first detection, which talk about a moment of like incredible excitement and wonder and just awe in pretty much the entire scientific community. That first observation was just amazing. It was so amazing because it was unequivocal. It was like the clearest possible example that you could have ever hoped for. I mean, it looked exactly like we thought it would look. It told us tons of information about the black holes that merged to create this gravitational radiation.
What does it tell us?
Well, it tells us their masses. So we know for those first objects that were observed that they were about each 30 times the mass of our sun, but very small, as also was mentioned earlier, I believe. So take something 30 times the mass of our sun and squeeze it into a ball that's like tens of kilometers, right?
When we look out into the universe, how far are we looking back?
So this is what Webb is trying to do, trying to push that limit. So with Hubble, so we measure this in terms of time after the Big Bang, because then you'd measure distances, there are too many zeros, it becomes hard to handle. With Hubble, we could look as far back as about 500 million years after the Big Bang. With Webb, the goal was to look back 250 million years after the Big Bang. That sounds like a long time after the Big Bang, but
why that number?
That just happens to be the limit because of the size and the power.
We'd take a smaller number if we could.
Yeah, of course. But in those few millions of years, a few hundreds of millions of years, the universe was quite active and still full of mystery. We don't know how those first few stars and galaxies were created, were born, so we want to have that information. And already, in less than a year of operations, Webb has almost reached its goal already. And if you take the entire history of the universe, nearly 14 billion years, and you put that on a calendar year, and you put us, modern time, at the end of that, December 31st, almost midnight, Webb can look back in the calendar year at the equivalent of January 6th. So that's really far back into the history of the universe.
Wow.
Yeah.
That is so cool. So, Bryan, what is the universe made of?
Well,
we don't know for the most part.
So this is a little bit embarrassing in that most astronomers study objects that are made of the same things as us. Like stars are made of the same things as us. They're made of protons, electrons, and neutrons. And I've spent my whole career studying various types of objects that are made of the same stuff as us. But that's only a tiny fraction of the universe. I figure, what's the latest percent of normal matter? It's not a big number, right? 4%, yeah. So 4% of the universe is made of stuff like us. And the rest is made of two things that we really don't understand at all, dark matter and dark energy. And I think most people think they're possibly not related, even though they have similar names.
Well, tell us the differences.
So dark matter is the easy thing to understand, even though it's one of the biggest unsolved things in science. So as far as we know, dark matter is some sort of other substance, some other type of objects. We're made of protons, electrons, and neutrons. So it's something else besides those. And we experience two main forces in our lives, and Nathalie mentioned this earlier. There's gravity, which holds us to the Earth, and every other force we feel is the electromagnetic force. So when I feel my hand on the desk, that's electromagnetism. When I feel the wind blowing on my face, that's electromagnetism. Dark matter feels the gravitational force, but it doesn't feel the electromagnetic force. And what that means is that dark matter can go through walls. Like if there's dark matter in this room right now, it would just sort of sink down to the center of the Earth. It feels gravity, and it's attracted by other mass, but it cannot feel the electromagnetic force. And that means it goes through everything. It means we can't see it. And it means if you try and observe it with a telescope, it just goes straight through it and out the other side. So this is really frustrating. We can only see its indirect effects. And when we look at groups like the Stephan's quintet that we looked at earlier, their orbits tell us that there's all this extra mass both within each galaxy and in the group of galaxies, and that's this invisible dark matter. So that's the easy problem, in that there's this whole nother set of particles that we don't know what they are. And then the even more mysterious thing is there's this dark energy which dominates the universe. I think it's almost 70%, 68% or something. And that's, Matt can correct the mess I make here, but my limited understanding is that it's
Limited understanding.
It's some sort of anti-gravity field which is sort of pushing the universe apart and making it sort of not just expand, but expand faster and faster. And that, if you were a visitor to our universe and said, what do we got here? You would say, well, there's dark energy and there's dark matter, and that's pretty much it. And then you go, oh, yeah, I guess there's a little 4% there. And that's planets, stars, birds, people, galaxies, everything else.
We really are insignificant.
Yeah, so I don't know if you can probably fix the mess I made there and sort of give a
let's fix the mess. So, dark energy is probably, I think it's the most interesting thing in the universe.
Why?
It's a property of empty space. So it seems that in the universe we inhabit, empty space has this property that it's endowed with a number. Okay, let's say the magic number is 2. Okay, and if I stretch space, then I always find there is this stuff that has the same value, or it has the same property, no matter how much I stretch space. And that's really weird, because if I made the room that we're in twice as big, say the density of the gas in this room would go down. But the density of dark energy does not go down. It is undilutable. It's undilutable stuff. And it's very interesting because it possibly connects with so many other parts of physics. For example, the reason that we think the particles that we're made of, the 4%ers, is because of something called the Higgs field. And this is another property of empty space. It's endowed with a value, and that tells the particles that we're made of what mass they should have. How much inertia does it take to move them around? And so you have this connection between the world of subatomic particles, things that we're really used to and we measure really, really well, and the cosmos. So there's a connection there.
4%ers, another title for a book.
Yeah.
We talked about technology, and Bryan, you're working on the CHIME project, a Canadian radio telescope. Could you explain what fast radio bursts, or FRBs, are and why more reports of them?
So that's a very easy question. The answer is we have no idea what fast radio bursts are. I think these are one of the most exciting things in astronomy right now. What was discovered in 2007 is that about once a minute, somewhere on the sky, there's just some random, incredibly powerful burst of static. So, if you take your car radio and you put it between stations, you hear static. And some of that static is coming from the sky. The sky naturally produces radio waves. And if you were pointing your car aerial at the right place, at the right time, you would hear this sudden loudening of the static as this fast radio burst. So you can sort of think of it as like a flash of light, but in the radio part of the spectrum. And so this is happening once a minute randomly over the sky. It's been happening once a minute for the whole of human history, but we only noticed this in 2007. And these are incredibly powerful. Like they put out much more energy than the sun by like a factor of 1,000. And we've now measured the distance of these fast radio bursts, and they are very far away. Some of them are hundreds of millions or even a billion light years away. And we have absolutely no idea what they are. So this is some sort of fundamental process that's happening all over the universe. Once a minute, somewhere in the universe, something incredibly violent happens. And we do not know what it is. So there's all sorts of theories. Some is that it's some sort of mega solar flare from a star that's obviously giving out a much more powerful solar flare than the sun could. Others is that it's like two very energetic objects colliding. Others is that some sort of explosion. At first, the explosion model was very popular, but then a few years ago, people discovered that some fast radio bursts repeat. So you don't just see that flash, you never see it again, but if you wait a month, that same one does it again. And so those can't be explosions, because if it's an explosion, there'd be like nothing left, you've blown it up. So those are some sort of object that's able to recharge and do another one and another one and another one. But there are others that only ever do it once. So maybe there's multiple types of fast radio bursts. But the idea that there's just something that we cannot figure out, I find very appealing, because normally when we find something new in astronomy, it's exciting and mysterious for like 6 months or even 1 month or even 1 week, and then some smart person says, I know what this is. And then there's this, everyone goes, you are right, and all of a sudden, mystery solved. But we have found fast radio bursts 16 years ago, and we still have no idea
what they
are. And so it's a mystery that's been much more persistent than most. So I'm really enjoying the ride and watching the field evolve. And I'm also just really relishing the fact that it's Canadians in the driver's seat. We've found 95% of all the fast radio bursts ever found. We've found thousands of them. Other people get excited when they get to 10. Every time we pass another 1,000, we all have a cake together.
Well, Walter, I have to ask you for the final question. Are there aliens out there? Is it aliens?
I'm not convinced it's aliens. I think we don't have any evidence of anyone out there or anything else out there. I know there's always imagination. There's always ways to think about what might be, but I think we'll discover that it's something really exciting, really fascinating. I don't think it'll be aliens.
Well, I mean, I think a lot of us get that because of the movies.
Of course.
And so in our final conversation, we're going to talk about what Hollywood gets wrong about space. Thanks again for another incredible discussion. We really appreciate it. Our guests all this week are
Bryan Gaensler, Director of the Dunlap Institute for Astronomy and Astrophysics, and Canada Research Chair and Professor at the University of Toronto. Astrophysicist Nathalie Ouellette, who is Deputy Director of the University of Montreal's Trottier Institute for Research on Exoplanets, and Outreach Scientist for the James Webb Space Telescope in Canada. Walter Stoddard, Researcher Programmer and longtime science communicator at the Ontario Science Centre. And Matthew Johnson, Associate Professor of Physics and Astronomy at York University and Research Associate Faculty at the Perimeter Institute for Theoretical Physics.